record, yeah. So I'm starting to record this class. We should have 40 students. Still half of the students is not here. But anyhow, I'm going to start sharing the screen. I'm just to sort out the message box and the participant list. So I should be able to see your message, but sometimes if I concentrate on the content, I might miss your message. So you can just unmute yourself and talk if you have some question that related to the subject, or if you have any issues. Okay, don't be afraid to stop me. If you send a message, that's okay. I will try to kind of have a look at the message box like from time to time, but sometimes it's just a small box at the corner, so I might not kind of notice it. So can you all see my screen? Everybody?
Yeah, we can see it.
Yeah, all good? I'm just trying to adjust the size so I can see everybody. Okay, so this is mech470 970. We call it advanced mechatronics topics. My name is Stephen Pan, so if you wanted to talk to me, don't call me teacher or professor or something else, just call me Stephen. Just make both of us more comfortable. How do I move this thing around? So this week will be just introduction. In the recorded video, I already kind of lay out what's going to happen for the subject. This subject is a bit special. The feedback I got from all the previous year students, this is kind of most interesting and most interactive hands-on subject you ever going to do in the university. So we used to have only 5 weeks of lecture, then the rest of them is all labs. However, this year things have to change a little bit. I've got a survey from you guys, and the feedback shows there's a few students are not in Australia, and a few students live like at home, not around Wollongong area. So plus the university has put quite strong limitation on how many students can be in the lab, and due to the lab setup we have, looks like if we're going to do lab, I can only have 4 or 5 students doing lab at one time, and each lab is going to take 8 hours. Then if we have 40 students, then that's going to just take forever for all you guys to do the lab. And because the university is also cutting the lab supervisors' hours, so it just doesn't add up if we keep doing that normally. So at the moment, we are trying to develop a few kind of simulations or computer-based programming to simulate what's going to happen in the lab. And the best we can do is maybe one of those 4 tasks in the lab, I will make it kind of available for you guys. Depends on how this virus situation goes. If it stays like current situation, I think it's probably fine. If situation gets worse, then probably that's not on the table. So I'll see if possibly you can be in small group, like group of 2, then go to the lab, just do one small task, like maybe 2 hours. If that's not going to happen, then what we're going to do is we're going to record some videos of the tutor going through the labs step by step. And then during the lecture or tutorial time in the later weeks, normally that lab week happens from week 9 to week 13. In those weeks, during the class, we're going to show you some videos, and maybe we can record on site. The tutor can do the operation, and you guys can ask questions or kind of interact with the tutor while they are doing some of the tasks for the lab. So that's something to give you probably the best hands-on experience for the PLC equipment, and also some kind of tasks that's very similar to the actual industrial control situation. So for you guys, what you need to deliver or what you need to submit will be separate kind of PLC programs, but with the simulation only. So we're still trying to develop those tasks. These tasks will be kind of starting from week 9-ish, so we still have plenty of time. So what is this subject all about? We are trying to bridge a gap between the control theories that you learn from the other class. How many of you guys have learned some control theories? Say classic control theory, say PID control, or what do we say, the Bode diagram, the Nyquist diagram, those things, the classical control theory. Yeah, I think all the local students must have done that in mech470. Okay, how many of you guys haven't done any control theory, have no idea what control theory is? Okay, still, yeah, XT344, that's perfectly suitable. And the mech470, those two are kind of equivalent subject in UOW to cover control theory. But I see one student haven't done any control theory. There's another one, particularly master student. If you are not doing bachelor degree in mechatronics, then or in electrical, then you might never know what control theory is. So you don't have to worry. This is what we do in this week. I give you an overview of control theory. We're not going to get to do any details, because when you actually program PLC, you don't need to know too much about control theory. Only the very basic idea would be enough, because we're not going to design a PLC based on some Bode diagram or root locus analysis. We're not going to get that far. We're only going to do PLC to program very basic kind of feedback control, but with very simple logic, without any Laplace transform and things like that. So that's fine. However, if you know a little bit about control theory, you know why this subject is here. Okay? So after you learning this 344 or mech470, you pretty much know if you are getting a transfer function, how do you actually calculate to design a controller that make it stable. That's what you got. However, after that, how do you actually implement a controller? Okay, so where are these controllers physically sit? That's what this subject is trying to cover. So one of the options for those controller to be implemented is through PLC. Now, there's other kind of method you can implement a controller. Depends on like different control theory, different control method. There are analog or digital methods that we can implement the controller. So PLC just one of the kind of digital ways. PLC, if you consider it just a computer with kind of special stress in kind of I/O and communication. So that's just what it is. A little bit more powerful than a microcontroller, but there's no way to compare to a normal computer. So it's special designed kind of industry computer with a very strong in communication and input outputs. Because when you in industry environment, the kind of most complicated situation is you have to talk to a lot of things, try to control a lot of switches, talk to a lot of sensors, communicate between many different instruments. So that's why PLC is strong at. Okay, so today I'm going to go through some of the review of control theory. That's going to take an hour-ish, and then introduce some of the basic example. One probably basic example where the PLC come from and why do we do PLC. Some of control system terminology, classification of control methods, and the requirement for control system, and some examples. And then going to do the second part is just introduction to PLC. So why do we get PLC? When did it happen, and what it is? Okay, so like I said, this subject is trying to bridge a gap between your theoretical kind of control theory to the actual industrial implementation. So in real situation, you probably never, or I wouldn't say never, but in very few situations, you're going to use a very complicated control theory. It's all going to be quite straightforward, quite clear kind of logic, but it's involved actual implementation. So that's this subject is about. But we are not going to train you to become a PLC programmer. That's what TAFE do. Okay? So the PLC subject is kind of one of the important subjects when you go to TAFE to do some electrical or control kind of area. So we are not going to train you to become a PLC programmer, but if you are very cluey, so through this subject you will be quite good at PLC program. But the purpose is mainly for you to understand what is there. And if somebody, some of your kind of engineer work with you is a PLC programmer and trying to program some stuff, and you know how to talk to them. Okay? You know their terminology, and if you become a supervisor in the future, you know this is an area about controlling using PLC, and what are the things related to that. So it's more from getting an overview, and you get some direct feeling when you go to the job place. This area, you're not kind of shocked. You're not kind of very naive in this area. Okay, so I think a lot of students appreciate this kind of feature of the subject, and actually spend quite a bit of time to do things by themselves. So kind of you can just go to internet, find a lot of related resources, because PLC program basically is a programming, and for any type of programming, the best way to learn is actually do some example and do that by yourself rather than have somebody to teach you. So you can find a lot of internet resources related to this subject. Although we have a textbook, but I don't recommend anybody to get a textbook. Basically what you do is you download some menus from that particular PLC, go through the menus, and then you go to YouTube or just Google some kind of questions. If you have any question, then you work that out by yourself. The subject itself trying to guide you through those steps, give you some important kind of information about a few things to help you to go through that process. So the first part of the subject, we're going to go for PLC. That's from week 1 to week 5. Yeah. So there will be basic stuff about PLC. So we're not going to do any programming. It will be all pen and paper, trying to work out the basic concepts, the logics about the PLC. Then from week 6 to 8, we kind of jump to another topic. It's also about a control. So other than using electronic circuits, we can also use a pneumatic circuits or pneumatic system to do the control. And also another important concept is hydraulic system. So we're going to cover this pneumatic hydraulic system in week 6 to week 8. And this part is also very relevant to the industry. There's a lot of pneumatic hydraulic equipment in the industry workshop factory. So give you some basic ideas, and also through this you will learn how to read those circuit diagram, how to draw and design a certain simple logic Once you get to find a job with something related, then you don't get the kind of shocked by kind of knowing nothing about that. Then week 9 to 12 will be some simulation or experiments, as we kind of explained at the beginning. The assessments, we will have 2 quizzes. So first quiz will be around week 6, I think, week 7 maybe, about all the PLC based concepts. That will be 15%. And the second quiz will be about pneumatic hydraulic materials. So that will be another 15%. Then we'll have 3 assignments or report with your kind of programming of PLC and simulation of the PLC tasks. So I will still have you guys in group of 2 students or 3 students to do this practical. So I'll send out some kind of tables for you guys to organize groups. It's still a few weeks away from now. Then we'll have a final exam. So in the previous years, all these exam quiz are kind of halfway open book. You are not allowed to read the book, but you're allowed to refer to 1 page of writing notes. And this semester, I will just make them open book. You can read any materials you like, but the arrangement would be I'll have 1 hour during the lecture time, and you come and log in the Zoom, turn your camera, then you just do 1 hour quiz. The quiz will be available from Moodle website. For some questions, multiple choice, then you just do the quiz on the computer. Other question you have to draw and write. Then what you do is you read the question on the PDF I upload from on the Moodle. Then you write down all your solutions and take photo, then submit the photos of your handwriting solution back on Moodle. So those are the ways we sort out this quiz and the final exam. Final exam will be arranged by the university, but will be similar kind of format. So far, any questions? No, all good? Yeah, all good. That's good. Nobody fell back to sleep. That's good. So I'll just go through some of the basics about control theory. If you know that, probably still, I think even you learn the subject because I'm putting 2 or 3 different subjects content in like 1 hour, still was listening. So for a system to control, normally the object of any control system, let me do some highlighting if I can. So the object of our control is has different names. Normally we call it a process or a plant, or we can call it different things. But it's a device, a process that we wanted to running under our kind of desired output. Okay, so if we don't control it, we generate output its own way. But when we have some control device before that, we want that output to be the value that we want. So for example, if a DC motor, normally the output speed is proportional to the voltage we're giving. So we can change the input voltage and trying to control the rotational speed of that motor. Also, we can call the controller, also we can call it compensator. So it is mostly algorithm. So in most situations, it's a software. In the older days, there can be a hardware, can be analog circuits with capacitors, resistors, and operational amplifier, and inductors. So you can use those analog circuits to do a controller. But nowadays, mostly it's a piece of algorithm or software sits in a computer somewhere. There are basically two types of control: open loop control, closed loop control. Normally, we only consider closed loop is control. Open loop, we don't really even call it control. So what is open loop? Means we want to generate certain output. Okay. So for example, if we have a washing machine, we want a washing machine to wash the clothes to clean. But if the clothes is like in different situation, we don't know how long we need to wash it. Okay? If it's super dirty, you might want to wash it longer time. When it's quite clean, you don't need to wash too long. So what we do is we ignore what we want. We just set up the controller, say this is just physical time. Okay? No matter how dirty the clothes is, we say the cycle will be like 30 minutes. Then just let it go. If it's cleaned or not, after 30 minutes, the job is done. So that's the kind of open loop. We don't have anything to measure if the output is that cleanness, if that cleanness is reached or not. We don't do that. Okay, so we don't know it. Just do the preset time. Here is an example again. So for example, you got a toaster. This morning, probably you guys just a bit rushed, and you grab a bread and put in your toaster, trying to quickly eat a breakfast. And unluckily, you bought the kind of a thin cut instead of a thick cut. And the setting is from last week, and for the thick cut, okay, you are setting up to the 2 minutes instead of 1 minute, then your bread is burnt. Well, luckily nobody had that happen. Okay, so in that situation, this is the open loop. The operator, yourself, setting a time based on your assumption, based on your estimation, how long it may take to do the job, and let it go. Then the machine just keep running by itself. If your estimation or your expectation is wrong, then bad thing happen. Your breakfast is gone, and you're hungry to stay here for 3 hours. Okay, so that can happen. So open loop control needs to be based on an accurate model, an accurate expectation, or accurate kind of model of the process. You know, certain thickness of bread will take certain time. Then you can have a look at the bread and set a time. Then you got a quite good well cooked breakfast. Otherwise, if you have wrong estimation, then disaster happens. Here is a video about feedback control. Let me see, how do I play this?
Day is the world with you in it. A good day.
Can you hear the sound from the computer as well?
Yep.
Yeah, good.
Is a heart with no limit. Show me forever. Show me forever.
So this guy is trying to ride a bike with his girlfriend. See, in that system, what is control? You can keep the bike running in a steady speed, right? You bring is the controller, control what you do, and there's a tachometer. You can see the speed, and you can speed up, slow down with your hands. However, in a kind of realistic world, you have noise, always have noise, and what you planned is never going to be perfect. There will be some noise coming. It's part of your life. Then you have to make adjustment based on what the sensor tells you. Okay? So you have to make changes if the situation changes. This is more kind of industrial situation, and we'll keep watching until it's done.
If there's meant to be sound, we can't hear it.
Yeah, there's no sound at this part. I don't know why.
No worries.
Sound come back again. So in reality, after you learn all those kind of crazy control theory, 90–95% of industrial control is using PID control. Anybody know what PID is? I suppose you should have. Or we'll keep watching this. Okay, so the PID part I'm going to go through when there's a few slides to explain that in the later slides. But the idea is there's three components in the PID control: proportional, integer, and derivative. And each one of these gain will play different roles for your kind of control response. I'm going to explain that a bit later. So for closed loop control, what we can see from the example is there will be desired output. So this is what the system wants to go, and this is the actual output. And we normally use some sensor to measure the output, and this is a negative. Normally, the difference is the arrow. So if the actual output is not the same as desired output, we have some problem. We want to minimize it. That's why we need a controller is based on this arrow message to change the kind of output of the system. So that closes the loop. So the feature of this is to make things very, very robust. If there's any difference, that difference is going to change the system behavior, and until the kind of difference diminish to a certain extent, then the system will be stable. Okay, so the feedback is the critical feature of the closed loop system, and always negative feedback. If it's a positive feedback, normally it will be kind of exponentially increase the difference, and the system just go unstable. So this is just the different components in the control system. So there will be a system or plant. We can call it plant, we can call it control object. That's, for example, this is a DC motor. There can be a motor, can be chemical plant. This is a kind of a process that's running by itself. And we have desired output. Actually, desired output is the input of the system. That's also, we call it reference. Then we have a sensor, or is called a transducer or sensor, to measure the output. Then use the arrow signal here. This is the arrow signal to drive our controller. So depends on kind of where all these components sit. You can kind of categorize the system in different ways. So the main feature of control, feedback control, we require that is because two things. One is if the model of the system is not accurate. If we have a perfect model, then we don't need a feedback control. Like if we know exactly the toaster, how thick the bread is, require how many minutes, we have a table list in the kitchen, then you have a ruler to measure the bread thickness, then you don't need feedback because you know the time compared to how well it's cooked, then you just set a time. There you go, that's okay. The second reason is because of disturbance. Because during that process, some other things might happen. For example, if you're cooking your toaster, your power just be black out for say 30 seconds. Okay? So you're setting up your toaster to be say 1 minute, then you walk away, go to toilet, come back, you expect the bread to be well cooked. However, it's still not, because there's a blackout in between for 30 seconds. Or blackout is not a good disturbance. So we'll see if the kind of the coil inside the kind of your toaster, one of them is broken, so you only left have half of the power. Then your setting up is going to be wrong, and your bread is not going to be cooked. Okay, so there's disturbance, there's noise coming to the system, and what you preset, even when you have a perfect estimation of the model, might not kind of be always there. It might be kind of getting disrupted. And in that situation, you need a feedback to know how well the bread is cooked. So that normally is your eye. You look at the bread, is that cooked or not? If it's not, then I give it another 10 seconds. If it's still not, I give it another 10 seconds. You can do this kind of loop and then until it's well cooked. So mentioning this, we've done some of the basic subjects. I think most of you guys did this one. Anybody did other ones? Any of this subject? Any students done this? Probably very few, because these are all like final year subjects. Give you some kind of extension, kind of knowledge about control theory. 468 and 949, this is about state space representation of control system, and also we do digital control. I think 441 is the safety one for I think for neural network and fuzzy logic control, and 442 is computer-based control from safety. So those ones are more of, like we call it, modern control theory, with kind of a different set of mathematical tools to do the controller design. But however, it doesn't matter. These are not required in our subject. So for the classical, or we call conventional control theory, which we covered in 344, we did frequency response, Bode diagram, root locus. That's the mathematical tool we have, because the input and output for a control system, the relationship are complicated. In time domain, the relationship between input and output is a convolution. Sorry, I probably can't spell this properly, but it's a complicated integration relationship. So that's why conventionally we can't really do that mathematics in time domain. So people goes to the frequency domain and use a set of mathematical tools, analyze everything frequency domain, and the convolution goes from frequency from time domain becomes multiplication in frequency domain, which you can do quite easily. So that's why we go frequency domain, and we've got a lot of tools. That's Bode diagram, root locus, all those tools we can handle in frequency domain. You can use your pen and paper to do the calculation, it's only suitable for single input and output. single output because you get a transfer function, right? You get a transfer function. This is your output or OS. This is your input, or normally you get A and B, right? BS, this is AS. This is a transfer function. The top is the, we call numerator, bottom is denominator. So this is normally only get one input and then one output. And this kind of transfer function describes the relationship between output to the input. Okay. In the modern control theory, what we do is we have more powerful calculation tools. When computer happens, we can actually do quite complex calculation in time domain now. So instead of going through those not very intuitive kind of frequency domain analysis, we come back to time domain with the help of very powerful computer, come up with a method we call the state space method. Everything is back in time domain, and we can handle multiple input and output, not limited to just single input and output, and use matrices. Use matrices to describe the complete setup, not just the input and output, also the inside, the internal states of your system completely. So this is kind of more powerful, and you can control a better controller in this state space method, but it included quite a bit mathematics behind that, mainly the matrix manipulation. And the controller can be kind of controlled perfectly. You can get a perfect control output, provided that you can build your model accurately enough. So you have to be able to get to your mathematical model, normally is A for your system. If you have that, then you can do a perfect control. So this is also with the development of space industry, when in 1960s, people wanted to go away from the Earth, going to the space, and with those control of rockets and satellites, and the requirement is more of we have to actually get things done perfectly rather than consider how much it costs to do it. So in that case, with the state space method, you can get best control ever, but with a lot of calculation, a lot of cost to do the modeling, a lot of kind of a computer power to get the accurate model of the system and to model the system and provide a control, but you can get the best control output. So this is kind of what we call it modern control theory using the state space methods. So just I think one thing you have to remember, even you don't know how this state space work, is it requires an accurate mathematical model. Okay, if we go back to the classical control theory, particularly PID control, one of the main reasons that PID control is so popular is because it does not require a model of your system. If you have a motor, you don't need to know all the parameters of your motor. Okay, a motor is something easier to get those parameters. You can do the calibration and stuff quite easy. But if there's something complicated, it's very costly to get the model of system. However, if with a PID, just do the classic control, you don't need to know it. You can do try and error. With state space, you can't try and error because it's just too complicated. You must get an accurate model. So that's only suitable for things are worth doing. Okay, for things are so complicated, and the performance is requirement is very, very high. So it's the cost is sometimes become less important. Then you go to this classic control. So I think for most of us, I never actually during my work and doing my research actually use some of the state space method. But maybe most of you guys wouldn't even need this. We can also categorize the control theory into two different types. So one is continuous. So that's also kind of classic continuous control. The other one is discrete time control. Also, we can call it, we normally don't call it discontinuous. We call it computer control or digital control. So all those things we just mentioned is continuous time control. The reason is most of the object we want to control is continuous. For example, the motor. The motor is kind of continually changing speed. The output is all continuous. Like we drive a car, the car is kind of moving in a continuous way. So the physical system we want to control mostly are continuous. That's why we started with all our controls of continuous. But with the development of computer, more and more control system is implemented inside a computer, which is a digital system. You have had to sampling the signal. You don't have a continuous reading of the system. So another branch that to categorize the control system is based on if it's continuous time or discrete time. So discrete time system, again, you don't need to know too much. One of the important thing here is the sampling period. If you have a high enough sampling period, and there's another thing is your data. If your analog digital converter has enough bits, so you have enough accuracy of the measurements. If you have those two things are much higher than your system required control time for your system, then pretty much you can use the classic control theory to do digital control. You don't have to learn a new bunch of theory. You just do it all in the continuous time design, then just digitalize it. The only problem is when your sampling time or your data bits is kind of limited, then the performance of digital system and the continuous system become different quite significantly. Then you have to use those specific discrete time control system theory to address those issues. Okay. So that makes things quite complicated, because in continuous time you have like S domain, Laplace transform. In the digital time, actually there's some equivalent. It's called Z plane. Okay, don't want to get into there. In Laplace transform, it's still quite intuitive. You have left hand of your S plane is when your pose on that area it's stable, on the right hand is unstable. With the Z transform, everything kind of you go from a linear coordinates become a polar coordinates, things all distorted, become very much not intuitive. So we normally don't need to go that far. So if your sampling frequency is high enough, omega is your system frequency, system response time. If your sampling frequency is high enough, then pretty much just ignore this difference between digital and continuous. You can just use your continuous time system or control system design knowledge to design a controller, then just digitalize it, provided you have that computing power. For a digital control system, there are two components is additional. Digital to analog converter. This is when your controller is a computer, right? Computer gets a certain algorithm, then output is a number. But that number normally comes, this is the number, then the number, a number. It's kind of a number with a sampling time. So difference here is your sampling time, okay? Normally you can, so each signal is coming out with kind of discrete values. However, like our plant needs a continuous signal to drive it. So we need a digital to analog converter. So that normally you can use like zero or holder. So the individual point becomes kind of a stage, kind of zigzag waveform, and use that waveform to drive your output. So that's digital analog converter. And back to this, the signal goes to the computer is only those dots. So the sensor is measuring a continuous signal. Then we have to do, this is called a sampling, or a analog to digital converter. So you take some values out of this measurement. So this is also your sampling time. Then inside the computer, you are dealing with these dot values, okay, with a certain sampling time. This is just, you can consider it just an array of numbers. Then you handle this all kind of just through a computer algorithm. The additional components here is analog to digital and digital to analog converter. So if you have your sampling time t is small enough, then your bits of your AD or DA, this bits, is accurate enough, so then your approximation to the actual signal is good enough, then you just use a normal control theory to, control your system. Let me check the time. Probably we have a 5 minutes break.